let's talk a little bit more about a little bit more complicated mechanisms. Suppose we have a multi-step reaction where something like A is in fast equilibrium. So forward reaction K1, reverse reaction K minus 1, equilibrium with some intermediate I. And then there's a second step where then we form products. So this would be, equilibrium before second step. So we have some scenarios that are possible. So suppose that we have, let's say K2 is our slow step. So K2 is a lot less than K1 plus K minus 1. So it's fast equilibrium followed by a slow step. We said before that means that the K2 is a rate determining step, and that is true. But the problem is, if we want to express the rate, what this means for us is our rate is going to be K2 times I. So the problem is that we cannot, so this is the key part about our rate laws, cannot express rate law in terms of intermediate. So we have to figure out how to convert this into expression or rate law expression of A. Okay, so we'll do what's called the pre-equilibrium approximation. And then, so this approximation assumes that K1 again and K minus 1 are a lot faster than K2, so that A and I are in equilibrium. And so we don't, if this were the opposite case, like if K2 were very fast, we would convert I as soon as it's formed, and then A and I would never be in equilibrium, so we wouldn't be able to do this approximation. So only certain scenarios apply for what approximations that you're allowed to use. Okay, so with this approximation, what this means is that if you recall we talked about equilibria steps before, so what this means is that our equilibrium constant equals K1 over K minus 1, and this equals the concentration of I over the concentration of A. And then so what that means is that we can then express the concentration of I in terms of K1 over K minus 1 times the concentration of A. And then so easy peasy, what this means is that we can then substitute this thing into our rate law. And then what we get out is, therefore, our rate is going to be equal to K2. So K2 times concentration of I, which is K1 over K minus 1 times concentration of A. So that's the, and then this could also be equal to big K, equilibrium constant, times the rate constant times A. So this is our overall rate law. I won't do that for a pre-equilibrium approximation. Okay. And then one thing that you could solve for later on would be, we could always then express that A at times T, at time T equals our initial concentration of A minus concentration of I minus the concentration of product. So, so this is, so these are approximations that you might use if your reaction appears to be first order. So you can see here that the overall rate law is first order in A, but if you suspect that there's more complicated mechanism going on, you could think about proposing a mechanism where you have this sort of behavior and then trying to fit some following rate law to that. So if you can identify an intermediate, you can maybe calculate your equilibrium constant and then find this overall rate law. Let's do an example in our next video of the pre-equilibrium approximation.